All right, it's 11 o'clock here in Virginia, so I think it's time to get started on the first of what's going to be a multi-part webinar having to do with using multivariate statistical methods to analyze data using Statgraphics Centurion. Looks like we've got quite a good audience today, which is always exciting, as it does take some time, obviously, to go through and put these webinars together. My name is Neil Polhemus. I'm in charge of Statgraphics development and have been for quite a number of years here at StatPoint Technologies. I'd originally thought we could talk about multivariate data analysis in a couple hours, but as I started going through and looking at everything that Statgraphics offers in the way of multivariate statistics, I've decided it's going to be necessary to do this topic, this particular topic, as a multiple-part webinar. In fact, I suspect it's going to take me at least 3 days to cover what I'd really like to talk about in terms of multivariate data analysis. This webinar I would expect to go about an hour and a half. You are invited to use the facility of GoToWebinar to submit questions, any questions during the course of the presentation, and I will try after I've gone through my formal presentation to answer as many of those questions as I can. So go ahead and submit whatever questions you had, and we'll be screening those as we go through and trying to answer them afterward. Okay. Now, the topic for today's webinar is multivariate statistical methods. Multivariate statistical methods have to do with the observation and analysis, the simultaneous analysis of more than one response variable. Now, I've talked in the past in some of the previous webinars about things like multiple regression, where you have a collection of fixed variables, fixed x variables, that have an impact on a single random variable, a single response variable y. This is going to be a little bit different. What we're going to be talking about now is the case where we have multiple random variables, multiple responses, and we need to analyze those observations together, not one at a time. Now, in preparing the webinar, I went through an excellent book by Johnson and Wishern called Applied Multivariate Statistical Analysis. And they listed actually 5 primary uses of multivariate statistics. The first use they listed was that of data reduction, or some might call it structural simplification. That's actually going to be the primary topic that I'll be talking about today. We're going to start off today looking at a data set consisting of 8 variables. 8 variables that characterize various countries around the world, with the goal of trying to understand the relationships amongst those variables. Now, unfortunately, we're typically limited in terms of plotting to plotting either 2 or 3 variables, at least without some loss of information because of the physical natures of the screens on which we need to plot things. We can't easily plot 8 variables. So there's been a lot of interest over the years in trying to reduce 8 variables down to 2 or 3 meaningful summaries of those 8 variables in such a way that we can plot them and we can understand what's happening. So we will be talking today about procedures such as a principal components analysis, whose primary goal is to take and reduce the dimensionality of our data so that we can get a better understanding of what's actually happening. Another primary use of multivariate statistics, which will be typically the subject of, I think, what's going to be part 2, a second part of this webinar, which I'm going to do in December, has to do with sorting and grouping. Taking observations, such as countries, and multiple measurements of the countries and sorting them in some meaningful order or partitioning them into groups. And here we're thinking about cluster analysis, discriminant analysis, that sort of thing. The second major use of multivariate statistics. The third major use would be the investigation of the dependence among variables. When you have a collection of variables, some of which are likely to be good predictors of another, then there are a set of techniques that will allow us to build simultaneous statistical models for those multiple dependent variables. And as in most statistical methods, the goal is often of our analysis to do predictions, to be able to take a collection of data, build statistical models, and then make predictions about observations outside the data set that was used to create the models. And finally, the fifth use that Johnson and Wishart talked about was that of hypothesis construction and testing, where you may have formal hypotheses that you wish to test the statistical significance of. Okay. Today's lecture will not emphasize very much any hypothesis testing and construction. Today's webinar is more of an exploratory or data mining type of an application. Now, as I went through StatGraphics and looked at the various procedures that are available for doing what we would consider to be multivariate statistics, I found a lot of items on the different menus. If you look, for example, at the plot menu of StatGraphics, you'll see a section of multivariate visualization. You'll see 5 menu items, 5 different techniques which have been designed to help us visualize and display multivariate data. Now, I did talk about these in a previous webinar, but a couple of them, particularly the first 2, the scatter plot matrix and the parallel coordinates plot, are so important that I felt the need to show them to you today as a way of first examining the data set we'll be looking at. You also find various procedures on the Describe menu. In fact, the Describe menu has a section on multivariate methods. And there are 7 different selections: correlation analysis, principal components analysis, and so forth, all of which actually correspond to chapters of the Johnson and Wishart book. These are bread and butter multivariate statistical methods designed to do various types of analyses. And we'll actually be looking at the first 3 of those today, and in the future webinars be looking at the others. If you continue on across the menu in StatGraphics, you'll also see procedures for doing multivariate statistics in some of the other sections. For example, under Compare Analysis of Variance is the General Linear Models procedure. That contains the ability to fit and do a multivariate analysis of variance, a MANOVA, if you enter more than one Y variable. In addition, under Relate menu is the procedure for partial least squares, which also builds models for multiple dependent variables. Now, we won't be looking at those today, but we will be looking at those in a later webinar. Under Relate, there's a section on classification methods that contains a discriminant analysis and a neural network's Bayesian classifier. Those are procedures that are useful for classifying observations, for trying to divide observations into groups, and something that we'll be talking about probably in part 2. Another procedure we will talk about today, though, is a T-squared chart. There is a section under Statistical Process Control, under SPC, that deals with multivariate control charts. A T-squared chart, a multivariate EWMA chart. Now, those are procedures, they're under SPC because they're primarily used for monitoring multiple variables in a control chart type setting. But the T-squared chart is actually quite useful for other purposes. and I'm going to show you the use of the t-squared chart today for actually identifying outliers in a multivariate sense. So, quite a lot to talk about. There's also a package, a complementary package to Statgraphics that I wanted you to be aware of. There is a program called Uniwin Plus that was developed by my good friend Christian Charles at Sigma Plus in France that complements Statgraphics, actually reads Statgraphics data files and does certain types of multivariate analysis that Statgraphics Centurion does not. Sigma Plus is the primary developer, supporter, and so forth of Statgraphics in France, has worked with us for many years, actually has done the entire translation of Statgraphics, all of the documentation and the program into French. He's also developed a nice program called Uniwin, and I'll do a little bit of demonstration of that today too. It contains some additional features for things like principal components analysis, correspondence analysis, cluster analysis, some features that Statgraphics Centurion does not contain. It also contains some procedures which are not performed at all in Statgraphics, such as a multidimensional scaling, principal components regression, and so forth. So I'm going to spend a little time demonstrating for you what Uniwin can do, because it's very, very easy to take your data from Statgraphics into Uniwin and get some of these additional features. Now, the data set I want to look at today, which I thought would be something that everybody could appreciate, has to do with characteristics of various countries around the world. Incidentally, I have posted the data set here on our website on the webinars page so that anybody who cares to, after the webinar is over, can do their own analysis of the data. It's all data that I collected from the internet, all public domain data. This file consists actually of 21 columns, 227 rows. Each of the 227 rows represents a country, a particular country in the world. The 21 columns represent things like the population density, the amount of coastline, net migration, infant mortality, GDP, literacy, number of phones, amount of farmable land, birth rate, death rate, and also the division of GDP into agricultural, industry, and service sectors. I've had a lot of fun looking at this data. I think you'll enjoy it as well today. It demonstrates very well some of the capabilities of multivariate statistics. Okay, now what we'll be talking about today, as I said, we're going to deal primarily with the topic of data reduction and structural simplification. What can we do to take a large set of variables and reduce it into something that we can visualize, we can analyze, we can get insights from? And it's much easier to do that in 2 or 3 dimensions than it is in 8 or 12 dimensions. Particularly the procedures I'll be looking at today, I'll be looking at a correlation analysis, a partial correlation analysis. I'll be looking at a parallel coordinates plot, which is one of the visualization techniques we provide. We'll talk about a principal components analysis, which is the primary mathematical technique for reducing dimensionality. I'll look at the factor analysis procedure. I'll look at the multivariate t-squared chart, which, as I indicated, is a good way to find outliers in many dimensions. And then I'll spend some time at the end of the webinar demonstrating some of the additional features that Uniwin offers, particularly the ability to add supplemental variables to the principal components analysis and also their procedure for doing multidimensional scaling. Okay, as I said, fairly ambitious webinar, but only starts to scratch the surface of what StatGraphics offers with respect to multivariate statistics. Now, as I said, the country file offers quite a few variables that we could potentially analyze having to do with countries around the world. I decided to take, for purposes of this study, 8 of the variables. Now, these is data actually from approximately 2006. You know, it takes a while until you can get information you get about various characteristics. But the 8 variables that I decided would be useful to look at, first off, the first one is the population density. Population density is the number of inhabitants in a country divided by the number of square kilometers. Okay. Second variable I'm going to look at is the percent of farmable land, the percent of land that you can use for growing crops. We'll also look at the birth rate, that's annual births per thousand of population. We'll look at literacy, percent of population that's literate. We'll look at infant mortality, per capita gross domestic product. We'll look at the death rate, and finally agriculture, which is the portion of GDP attributable to agriculture. These 8 variables give me, I think, a pretty good set of data to look at. Now, in order to start this, I'm going to go over to StatGraphics, and I have already loaded into StatGraphics the data set on countries of the world. And the first thing I did with this particular data, these 8 variables, is to go to the multiple variable analysis procedure. Now, the multiple variable analysis procedure is on the Describe menu under Describe, Numeric Data, Multiple Variable Analysis. You can see it right here. Okay. I entered as the data that I wanted to analyze the 8 columns that I just listed on my previous slide. Okay. And what it gave me by default is it gave me some summary statistics for each of those 8 variables. It gave me a correlation matrix, and it gave me what's called a matrix plot. Now, I'd like to start by actually looking at the matrix plot. The matrix plot is a very interesting plot. It gives me my first view of those 8 variables. Okay? The way it works is this. On the diagonal of this matrix, you see the 8 variables: population density, amount of farmable land, birth rate, literacy, and so forth. You also see underneath the name of the variable a box and whisker plot. Now, for those of you who aren't familiar with the box and whisker plot, a box and whisker plot is a very nice way of summarizing a set of data. The box itself covers the center 50% of the data. There's a vertical line, and I'm looking at infant mortality, for example, a vertical line at the median, a plus sign at the mean, and then whiskers down to the smallest observation on the largest observation, unless there are certain points too far away from the box, and they're shown as individual outside points, as individual symbols. Now, if you look at something like infant mortality, you notice that that data set is quite skewed. Okay? Half of the data, half of the countries have infant mortalities below the median line, very close together, while the other half are spread way out to the upper end. Okay? Highly skewed, that particular data set. And in fact, if you look at any of my variables, population density, farmable, pretty much every one of the variables, the distributions are quite non-symmetric. Now, I'm not going to be doing a lot of statistical tests. I'm not going to be assuming that data necessarily come from a normal distribution. However, I am going to be using statistical techniques, okay, that will
create linear combinations of the different variables. And if the data are highly skewed, okay, then the outliers are likely to have more impact than they should on the representations that we'll be coming up with. Okay. You can also notice there are also a lot of nonlinear relationships. On the off diagonals in the matrix plot is a scatter plot of a particular pair of variables. So for example, if you look at this plot right over here, this is a scatter plot where infant mortality is on the y-axis, GDP is on the x-axis. And I've put a lowest smooth, what's called the lowest smooth, through that data to, in a non-parametric sense, show what the relationship is between infant mortality and GDP. Well, you may notice that actually that's quite nonlinear, and in fact there are a lot of nonlinear relationships in this particular data. That's also going to make it more difficult for the statistical techniques that we want to use to summarize what's going on. So before I actually do a principal components analysis or anything like that, I thought it would be useful to take this data and make the distributions of the samples a little bit more, if not normal, at least symmetric. Now there's a very nice procedure in StatGraphics that will help you do that. If I go to the Describe menu to Numeric Data, where is it? Here it is, Power Transformations. I can take any particular variable, for example, infant mortality, put it in the data field and press OK. Okay? And taking all the defaults, what StatGraphics will do is it will apply what's called the Box-Cox procedure to suggest how I might transform that data to make it more symmetric. And in fact, you can see right here that it suggests that I take infant mortality, raise it to the 0.002 power. Okay? Well, anything close to 0 in the case of the Box-Cox transformation implies that what I should do is take a log. Okay? In fact, the confidence interval for the power definitely contains 0. So the definite suggestion that taking the log would be a good thing to do with infant mortality. Over here, incidentally, it shows you what a normal probability plot would look like if we took infant mortality and raised it to the 0.002 power, approximately took a log. Normal probability plot is a plot which, if the data followed a normal distribution, the points would all lie along a straight line. Well, this is not a perfect transformation for normality, but it does at least make the data much more symmetric than it was before. In fact, this sort of normal probability plot shows that, in fact, the core of the data is distributed similar to what we would see from a normal distribution. This curvature of the tails here indicates shorter tails than a normal distribution. But again, we're not going to be doing a lot of statistical tests. What we're trying to do is spread out the data, okay, so that all the points can have approximately equal leverage on what we're looking for. Well, it turns out that I did this analysis. I did it for every one of the variables. And you can see a table here of what I found when I analyzed the 8 variables. Now, the table includes several interesting statistics. You see the 8 variables listed, one in each row. The column that says standardized skewness measures the skewness of each of the variables before I took any sort of transformation. This is a statistic that multiple variable analysis shows in its summary statistics table. And the way we interpret standardized skewness is that if data come from a normal distribution, that number should be between -2 and +2. Well, none of the variables, none of them, have a standardized skewness between -2 and +2. So none of them look like they could have come from a normal distribution. In the next column, you see
the results of running that Box-Cox procedure on each of the variables. I've listed what the power transformations procedure suggests would be the optimal powers. I've also listed where it said selected transformation, what I decided would be, based upon the Box-Cox procedure, a reasonable transformation to do. Now, I don't believe, for example, in taking something like population density and raising it to the 0.027 power. However, something very close to that, something like a log, will help me get a good representation for the data. And you can also see over here in the far right what the standardized skewness was if I took my transformations, and in actually 5 cases I decided on a log, in 1 case a square root, 1 a cube root, 1 a cube. And for everything except literacy, it actually did a pretty good job of getting rid of the skewness. Now, literacy, even when I cubed the data, was still somewhat negatively skewed. But I really hated to go to anything stronger than that. I thought it really might distort things. So those are the transformations that I decided to do. Well, if I go back to StatGraphics for a moment, let me go back to that, well, actually to the data file itself up here. Okay? And I'm now going to, in place of this original data, load up a data file called Countries of the World Transformed. Do I want to replace the data in sheet A? Yes, I do. Okay. What this is going to do is it's going to load a second data file. This is the data file where I've taken each of the variables and I've transformed it. For example, here is infant mortality in the log scale. If I now go back to the multiple variable analysis, it will have updated the plot based on the different transformations that I've assumed would be good for this particular data set. Okay, and you can see now much better symmetry in most of those box and whisker plots. You can see that the whiskers are about the same size, the median's right in the middle of the box, and so forth. You can also see that the relationships amongst the variables are now much more linear than they were before. Okay, you see, for example, the relationship between infant mortality and GDP is very nearly that of a straight line, whereas before it was definitely nonlinear. Now, what this has done is it's really spread out the observations and simplified the relationships so that I will be able to better visualize things and that things won't be distorted by those observations which were so far away from the others. Okay, it takes a little time to get your data in the shape that you want, but it's quite necessary before you try to make any conclusions. So incidentally, as I go ahead, I will still call the variable infant mortality. It's actually, though, the log of infant mortality and GDP, the log of GDP. But to keep the variable names short and so forth, I left them with the names that they initially had. Okay. Now, those are the 8 variables transformed in such a way that each of the samples is reasonably symmetric and most of the relationships are linear. I'm now going to go over to the table in the multiple variable analysis that estimates correlation coefficients amongst the different variables. Okay. Well, what you see here is actually a correlation matrix where you have various cells showing the correlation, the estimated linear correlation between every pair of variables. For example, the way you read this is if I go to the row labeled infant mortality and then I read over to the column labeled GDP, you will see that infant mortality and GDP have a correlation of about minus 0.86. That's a reasonably strong negative correlation, quite strong negative correlation. In general, as GDP goes up, infant mortality goes down.
It's probably not too surprising. It does sort of make sense that the wealthier the country, hopefully the decreased level of infant mortality. That incidentally is based upon 224 pairs of observations, pairs of countries. There were 224 countries that had information on both infant mortality and GDP. If I wanted to do a formal statistical test, if I wanted to test the hypothesis that there was no correlation, and if these were actually random samples from a multivariate normal distribution, which would be an unlikely assumption, this would be a p-value associated with the t-test of whether or not there was a significant correlation. And in fact, that correlation with that amount of data would have been highly significant. In fact, you see an awful lot of red in this table indicating that there are significant correlations amongst pretty much all the different variables, except, for example, for farmable land. Farmable land here is not very highly correlated with much of anything, except one thing. The amount of farmable land a country has seems to be positively correlated with its population density. The more farmable land, the higher the population density. The other procedures, other variables, not very strongly correlated with the amount of farmable land. Now, this correlation matrix is key because it captures all the relationships amongst those 8 variables. Now, another table you might be interested in looking while we're in the multiple variable analysis procedure is the partial correlations. The partial correlation table shows me the correlations between pairs of variables, correcting for the effect of all the other factors. Okay? For example, if I look at infant mortality and GDP, they have a partial correlation of minus 0.39, considerably less than the minus 0.89 they had before. What we do, though, is we would interpret this partial correlation as showing how correlated infant mortality and GDP are if we take out the effects of all the other variables of population density, farmable land, birth rate, literacy, and so forth. So it is, in some sense, the unique correlation between those variables. And there is still some unique correlation between GDP and infant mortality, although it's not as strong as the straight correlation itself without doing that correction. Okay, well, enough for the multiple variable analysis. The next thing I thought I would do with this particular data was to do a little visualization. I'd like to go to the plot menu to multivariate visualization. And you see, for example, a parallel coordinates plot. Now, actually, let me go back to the data input screen for multiple variable analysis. Take those same variables. I'm going to do a Control-C to simply put those names on the clipboard. And then I'll go to plot multivariate visualization partial coordinates plot. Do a Control-V to place in the names. Okay? Just a quick way of taking a set of variables from one procedure to another. I'm going to ask it to basically color code the data by region of the world. If I press OK, it's now going to create for me what's called a parallel coordinates plot. Now, before I do anything else, I'd like to go to the x-axis, slant those labels, so that they don't overlap each other too much at the bottom. Okay, now this is a plot of actually all those countries which have complete information on the 8 variables. There is some missing data in this particular data file, and in fact, only about 179 countries have complete information. What it's done on the parallel coordinates plot here is it's taken each one of the variables, for example, infant mortality, and recoded infant mortality from 0 to 1. The country with the lowest infant mortality, it coded as having a 0. The country with the highest infant mortality got a 1. Okay. Obviously, everything is measured in very different units, so to put it on a single plot and make some sense of it, we've got to somehow code things. Then we've taken every country and drawn a line connecting its population density with its farmable land, with its birth rate, literacy, and so forth. Now, what do I see? Well, I see what looks initially to be fairly confusing. There are some obvious things, though, you can see in this plot. Take a look at the variables infant mortality and GDP, for example. Notice how the lows become high and the highs become low. This sort of crossing that I see in all the lines indicates a quite strong negative correlation between the variables. On the other hand, if you look over here at population density and farmable land, you see that most of the lines are sort of horizontal. Okay, you have similar values for population density and farmable land. So there's a positive correlation between population density, farmable land. There's some strong negative correlations amongst all the other variables. As far as the individual regions, there's just too many regions, unfortunately, on this particular plot, too many colors that are similar to see much. However, there are some things I can do to make this plot a little bit more meaningful. If I go back to the data input, for example, instead of using region as the code, I might type region equals, and then I'll do a quote, Western Europe, double quote. Region equals double quote, Western Europe, double quote. What that's going to do, that's going to result in a true or a false. A 0 for countries not in Western Europe and a 1 for countries in Western Europe. Okay. Now if I replot it, all of the countries in Western Europe are going to appear to be red. And you can see that there's a definite similarity amongst the countries in Western Europe. You look at the obvious pattern of the reds with respect to things like birth rate and literacy and infant mortality and GDP, and to some extent death rate and even agriculture. Where there's variability amongst the European countries, the Western European countries, is when it comes to population density and farmable land. You can see that they're not nearly grouped together as closely. Okay. That's a little bit more meaningful plot because we can begin to see, for example, the countries in Western Europe as a group. Okay, well, where's the United States? Well, the United States not in Western Europe, but if I go back to that data input, I'm now going to type, instead of just region equals Western Europe, I'm going to say region equals Western Europe, put quotes around that, plus 2 times, open some quotes, and put country equals, quote, United States. Okay? Now what that's going to do, that should add a 2 for the United States and add that to the plot. Let's see what that does. Okay? Well, that added another line. Unfortunately, it's a purple line, which is hard to see. But I'm going to right-click, go to Graphics Options, turn that purple line to black, and thicken it out. Okay, and now I have a black line for the United States. Okay, and you can see the United States is quite similar to Western Europe, certainly with respect to things like literacy and infant mortality, GDP, and so forth. has a little bit higher birth rate, though. I can see it's a little bit higher than most of Western Europe with respect to the birth rate, though otherwise fairly characteristic. Very interesting plot, the parallel coordinates plot, something that allows me to visualize in 8 dimensions. Okay, now, enough of that particular procedure. Let me go back to my PowerPoint slides for a moment. Let me go down a little bit and now talk about dimensionality reduction. Up until now, I've tried to plot all of the variables. This scatter plot shows all the variables, the matrix plot plotted as pairs. The principal coordinates plot connects all 8 variables again after putting them on a single 0 to 1 type scale. I now want to look, though, at the idea of reducing dimensionality. There is in StatGraphics, as there is in most statistical programs, a method of analysis called principal components analysis. Principal components analysis is used to explain the variance-covariance structure of a set of variables. And typically, at a set of data like this, it's going to do some mathematical operations on that correlation matrix, that table and that matrix of correlations that I showed you in the multiple variable analysis. In general, what PCA does is it converts a set of correlated variables into a set of linearly uncorrelated variables by taking linear combinations of the variables. Now, here I have x1, x2, up to x sub k, representing population density, amount of farmable land, GDP, and so forth. The principal components are linear combinations of those variables. Now, not of the variables, though, typically in their original units. Usually it's standardized values of the variables. A standardized variable is a variable where you take the actual value, subtract the mean, divide by the standard deviation. That basically makes all the variables dimensionless and on a similar scale. And often it turns out that if you look at the first several principal components, okay, which are themselves uncorrelated, that you can capture most of the variability in a larger set of variables using a small number of principal components. Primary goals of doing a principal component analysis is typically reducing the dimensionality of the problem, which makes it easier to plot things and interpret, for example, what's going on. A little bit more about principal components analysis. The way it's done is it starts off by looking for the linear combination of the variables that explains the largest amount of the variance. The linear combination that explains the largest amount of the variance is the first principal component. The second principal component is the linear combination orthogonal to the first that explains the next greatest amount of variation. And as I said, you can often, by looking at the first 2 or 3 principal components, capture most of the variability that exists in the data. And the important thing about that is it's much easier to visualize 2 or 3 components than it is 8 variables. It's just hard to plot things in an 8-dimensional space. We also typically use principal components to do things like build predictive models with a principal components regression, or as I'll show you in the next webinar, principal components are very useful if you're going to do something like a cluster analysis. Okay. Now, just to show you, give you an idea of how I like to think about the principal components, let me go back to StatGraphics. And let me do a quick plot for you. Let me go to plot, scatter plots, XYZ plot. And I'd like to do a plot where I'm going to take infant mortality, put it on the z-axis, GDP, put it on the x-axis, and birth rate, put it on the y-axis. Okay? This will do for me a three-dimensional scatter plot. Okay? Now, I'm going to start calling this scatter plot here a point cloud. It's a cloud of points with every point representing a country plotted in the space of GDP, birth rate, and infant mortality. Now, if I could, I'd make you an 8-dimensional scatter plot. I can't do that, but just for purposes of illustration, suppose I had just 3 variables. Well, what do you notice? Well, I think you notice that there are definite relationships amongst the variables here. GDP and birth rate and infant mortality. And if I asked you along what dimension does that data show maximum variability, I think you could probably look at it and say, well, Neil, if I took a line from here up to here in that 3-dimensional space, the points seem to vary most greatly along that line. Okay, well, that line is, in fact, the first principal components for those 3 variables. And then I could ask, okay, let's suppose there is a first principal component here. Find me a line, another line perpendicular to that first line, which explains the next most amount of the variability. That would be the second principal component. Okay? We're not going to do that, though, in 3-dimensional space. We're going to do it in an 8-dimensional space. And to actually do the principal components, I'm now going to go to Describe, Multivariate Methods, Principal Components. Actually, before I do that, I'm going to go back here. Go back to Multiple Variable Analysis. Make sure I pick out the right variables. Put them back on the clipboard again. I don't know if they're still on the clipboard. Now go to Describe, Multivariate Methods, Principal Components. Put in the 8 variables. And actually where it says point labels, I'll put in country to label the variables. Okay, and press OK. Now, before I actually do the principal components analysis, you're going to see that there are a number of options that are offered to me. The first option has to do with how I'm going to treat the missing values. Am I going to treat them in a listwise manner or a pairwise manner? Listwise would mean throw out any rows, any countries that don't have complete information on all the data. That is the default, and that's what I'm going to do. If you had lots and lots of missing values, it might be better to do things on a pairwise basis. Pairwise means for every pair of variables, excuse me, take all countries that had information on that particular pair. Only problem there is that every time it then computes a correlation, it's going to compute it based upon a different set of countries. So it seems to me that if you can, you'd like to do things on a listwise basis. The standardized option here tells me whether or not I want to work on the correlation matrix or the covariance matrix. If you click standardize, and that is the default, the first thing it's going to do is compute that correlation matrix and then do its mathematics on the correlation matrix. It certainly would make sense in this case where everything's measured in different units that I ask it to standardize the variables before it does anything else. The third thing I need to specify is how it should decide how many principal components to extract. Okay, and there's 2 ways of doing it. You can tell it extract based upon a minimum eigenvalue. Now what it's going to be doing mathematically is going to be computing the correlation matrix calculating the eigenvalues of the correlation matrix. And the default criteria is to extract as many components as there are eigenvalues greater than 1. Okay? There's some theoretical reasons for that. That may or may not be a good criterion in any particular case. I could also tell it by clicking the number of component fields exactly how many components I wanted it to extract. Okay. In this case, though, I'm going to take the defaults. I'm going to tell it extract as many eigenvalues as there are components greater than 1. When I press OK, it's just going to offer me various tables and graphs. Okay, I'm going to take the defaults and have it come up with an analysis summary and a scree plot. Now, the analysis summary will tell me something about what it's done with the data. There were, it says, actually 197 complete cases. It found 197 countries that had information on all those 8 variables. In the principal components analysis table, it's going to show me the eigenvalues, the percent of as well as the percent of variation explained by each of the components. Now, particular interest to me is going to be, I think, the percent of variation explained. It says that the first principal component is capable, in this case, of explaining 55% of the variability in all of those 8 variables. That's pretty good. One linear combination of the 8 variables represents more than half of the variance in all of those 8 factors. Quite a strong component in this particular data. The second principal component, there's a principal component orthogonal to the first, is capable of representing about 17.5% of the variability. Now, you'll notice over here in the scree plot where it plotted the eigenvalues that those 2 eigenvalues are greater than 1. So it decided, in fact, to extract 2 principal components. Now, there are other criteria for deciding how many components you ought to extract. Another rule is to look for a knee, a flattening out of the scree plot. I don't see any obvious knee in this case. I do see, though, that there also is a third principal component representing about 11% of the variability. And actually, if I was to take 3 principal components, together the first 3 principal components represent about 84% of the variability. Okay? So clearly, if I took 2, maybe 3 principal components, and I can plot things in either 2 or 3-dimensional space, I would be capturing most of the variability in this particular data set. Okay. Well, what else should I look at? Well, if I press the Tables and Graphs button here, another thing I might like to look at is the component weights. The table of component weights shows me the actual linear combinations of the variables that have been derived. Okay. The first, each of these columns where it says component 1 and component 2 shows me those P1s and P2s that I had shown you with a definition of the principal components. The Stat Advisor has actually listed out and written out the first principal component. Now, if you look at the principal component weights for the first principal component, you see that the largest weights are on birth rate, literacy, infant mortality, GDP, and agriculture. Some are positive, some are negative. because there's a negative correlation, for example, between infant mortality and GDP, so it's not surprising to see them with opposite signs. But basically, the first principal component is a linear combination, a weighted combination of birth rate, literacy, infant mortality, GDP, and agriculture. That's the percent of agriculture in the GDP. Now, if we wanted to try to interpret that, we'd probably say, well, that seems to be related to how industrialized a country is, right? How highly developed and industrialized a particular country might be. Okay. The second principal component, if you look at the weights up here, the second column of that table, the only high weights in the second principal components are on population density and farmable land. So clearly, the second component has to do with how dense the population is and how much farmable land there is in a particular country. It's always interesting to try to interpret those weights. Now, rather than looking at the table, of course, it might be better to plot this out, and I can do a 2D component plot. This will actually plot out the weights with respect to the first two principal components. And you can see very quickly here that variables with high weight on the first principal component, high positive weight are literacy and GDP. Large negative weight is on agriculture, infant mortality, and birth rate. Death rate is weighted a little bit, but not as much as the other factors. On the other hand, the only factors with large weights for component 2 are the amount of farmable land and the population density. Okay. Sorry, I was just checking if there were any questions that had been submitted already. No problem. Another interesting plot to plot out is a 2D scatter plot. The 2D component plot shows you the component weights. The 2D scatter plot will actually show you the locations of various countries with respect to those two dimensions. Now, if I go up on the analysis toolbar to the identification button, I can pick a country and actually tell it to click points to label the countries. Then if I start clicking on points, I can ask, okay, who's weighted strongly on the first component? Well, the country that ranks most highly on the first component is actually Hong Kong. Okay. The second here, well, there's Macau. The third is Singapore. Hong Kong, Singapore, and Macau are at the far end, positive end of component 1. Contrast that with countries down at the low end like Niger, Somalia, Sierra Leone, Liberia, and so forth. And I think you can get a pretty good idea of what that particular component is measuring. You know, how industrialized and developed a particular country might be. Okay. With respect to the second component, the highest country on the second component is Bangladesh. So I'm sure it's a very densely populated country. That we would contrast to a country down at the low end like Iceland, which actually obviously doesn't have much farmable land and is probably not very densely populated. Okay. That's quite a I think, a meaningful plot to look at. Okay. Now, if you wanted to find a particular country, for example, if I wanted to find the United States, I could also go up to the toolbar here, type in United States, and click the binoculars. It actually turned a point red, this one right there, so that is the United States. Okay. I don't know if you've ever used this facility to look for an observation, but if you typed in the name of a country up here on the analysis toolbar in the label field, hit the binoculars, it would actually turn a point red, which would make it easy for you to identify where the location of that is. So the United States actually ranks, is fairly highly ranked on the first component, and actually close to 0 or close to average on the second component. Okay. Now, there's another plot you might also like. It's called the biplot. And what a biplot does is plots both the variables and the observations simultaneously. So you can actually combine the component plot with the scatter plot of the countries. Okay. Now, one other thing I want to do before I leave the principal components procedure is I'd like to save the principal components. If I go to the analysis toolbar, there is a button that will save results. If I push the Save Results button here, select Principal Components, and press OK, what it's now done is save the principal components to the data book. Okay, it actually went in and in tab B of the data book saved the principal components. So you can see, for example, the first 2 principal components saved here for all of the countries. Now, I actually wanted to save more than 2, so I'm going to right-click, go to Analysis Options, and actually ask it to extract by number of components and tell it to save all 8 principal components. Okay, well, they told it to extract 8 principal components. I'm going to save results again and have it save the principal components back again. And now when I go to tab B, hopefully I will have, there I do, all 8 principal components. The first 2 are the same as they were before. I just wanted all 8 principal components saved for something I'm going to do in a few minutes. All right. That is the principal components analysis procedure, which is the first of the, well, not the first, but one of the primary procedures in StatGraphics for reducing dimensionality. A second procedure in StatGraphics that's useful for reducing dimensionality is something called a factor analysis. Now, a factor analysis does something very similar to a principal components analysis in that it tries to describe the variability amongst a set of correlated observed variables in terms of a smaller number of unobserved variables. But the thought process, the conceptualization of it is a little bit different. Instead of starting by writing equations for the principal components, we typically will start by writing equations for each of the factors. I'm going to take, for example, a variable like infant mortality. And I'm going to say we can write infant mortality, or at least the deviation of infant mortality from its mean, as a linear combination of common factors, which would be factors that were common to all of my variables, plus a specific factor, an epsilon, specific just to that variable. And I'm going to do this for each of my variables. Each of my variables is thought of as being a linear combination of some common factors, F, things that all the variables share in common, plus a specific factor, one for each of the variables. Okay? The nice thing about this is then we can later go in and ask, okay, how much does each variable share of the common factors, and how much is specific to that particular factor? Incidentally, when we write it this way, the coefficients are referred to as factor loadings. And we talk about how highly a particular variable is loaded on each of the common factors. Okay. Well, let's go ahead back to StatGraphics now, and let's do a factor analysis. Let me take the same variables that I've been using today for doing a principal components analysis, but do a factor analysis instead. Go to Describe, Multivariate Methods, Factor Analysis. I'm going to put in those 8 factors. Press, and also put in country for the point labels, and press OK. Now I'm going to get on the analysis options dialog box similar choices to what I had for principal components, except for a couple additional things. There's also an option for the type of factoring. Do I want to do a principal components factoring, which basically says the same mathematics that I was doing in the case of the principal components analysis, or do I want to do a classical factor? Principal components factoring will factor the correlation matrix, at least if you ask it to standardize as I'm going to. In the case of a classical factoring, you can actually replace the diagonal elements of the correlation matrix with estimates of what you believe the communalities are for each of the variables, which is how much does each variable have in common with all the others. Okay. Now, you would have to have some idea what those were to do that classical factor analysis. Another choice I have has to do with rotation of the factor loadings. Okay, I'll talk a little bit more about that. I'd actually like to take all the defaults here, except I'm going to change from Varimax rotation and to ask it to do no rotation. Okay? And I'll take all the defaults as I come in. Okay, now, what it's going to do mathematically, it's going to do an analysis similar to what was done in the principal components procedure. In fact, the table here is going to look identical to what it looked like in the case of the principal components. It takes, in this case, because of the way I've asked it to do things, the correlation matrix amongst all the variables, shows the percent of variability explained by each of the factors. I'll call them factors now. And again, we would choose to extract by default based upon the number of eigenvalues that were greater than 1. What's different? Well, what's different can be seen if I push the tables button and ask for extraction statistics. Okay? If I ask for extraction statistics, it will give me a table with those factor loadings. Okay? This table I can look at now and I can say, okay, how does each of the variables load on the different factors? Well, population density is loaded primarily on the second factor, farmable land on the second factor, infant mortality, on the other hand, loaded highly on the first factor and not much at all on the second factor. Okay? So you can see our thought process is a little bit different in that we're asking how is each variable loaded on the factors. Also of considerable interest is this table right down here. This table shows me the estimated communality as well as the specific variance. It shows me a proportional breakdown. You'll notice each of the rows, for example, here will add to 1. A proportional breakdown of the variance in population density between the common factors and the specific factors. So I would look at that line and say, 69% of the variability in population density seems to come from the common factors, about 30% from a specific component, just specific to population density. And you can see that 2 factors represent certainly a majority of almost everything except for death rate. Each of the variables, its variance, is pretty well explained by the 2 factors that we've extracted, except for the death rate. Only about 23% of the death rate is well explained by the first 2 factors. About 77% remains unexplained. Okay? Well, what can I do with that? Well, as you can guess, if I override the eigenvalue selection, if I go to analysis options and ask it to extract not 2 factors but 3, you'll see that the third factor, or third principal component, any way you want to see it, but the third factor would be loaded very strongly on the death rate. So perhaps there really are 3 important factors that describe the variability amongst my countries. 1, how highly industrialized it is. 2, how densely populated it is. And 3, what the death rate is. That's number of deaths per 1,000 population. What exactly that means, I'm not sure, but it's interesting, and that's what we're doing. We're exploring the data, mining it, hopefully to find little nuggets that we might not have anticipated earlier on. And by the time you do that, incidentally, you can see that the estimated communality for, not GDP, I'm sorry, death rate is now up to a good 90% once we put the third component in. Okay? Now, in a similar fashion to the principal components analysis, in the case of the factor analysis, I can ask for a factor plot. I can ask it to plot those factor loadings either in 2 dimensions or in 3 dimensions. Here it is plotted in 2 dimensions, a plot of the factor loadings. And you can see that this is very similar to the principal components plot, except for the fact that actually the sign of factor 1 is switched. And that's completely arbitrary, what's positive and what's negative. In this case, it's actually switched the sign of the first factor. So everything, this looks exactly like the principal components plot, except that we switched from positive to negative on factor 1. Now, this is the factor loading if I don't do any rotation. One of the things that a factor analysis does do, the next step that people often do, is to rotate these factors. Now, what we've actually done, one way to think about it, is we've taken points plotted out in n-dimensional space, and we've projected them down to a 2-dimensional plane. Okay, so we've taken points in 8-dimensional space, projected them down to 2 dimensions. Well, any 2 lines in a 2-dimensional space will define that plane. So the factor loadings that one come up with, it turns out, are not unique. We can find other sets of factor loadings that represent the same amount of common variance. And in particular, we can take these axes and we can rotate them. And one way to rotate them is actually to push the analysis options button and ask for a Varimax rotation. A Varimax rotation will try to maximize the differences amongst the factor loadings. It'll try to drive some loadings to 0 and make others large. If I ask for a Varimax rotation here, it'll actually rotate the axes a little bit, which it looks like it rotated the factors, but it actually rotated the axes. And often that simplifies the definition of the factors. Now, it was pretty clear, I think, to me what the different factors were here even before we did a rotation. But there are cases when, by rotating things around, it makes the definition of the underlying factors more clear. Okay. Well, that's a factor analysis. Now, let's go back for a moment, if we can, to my PowerPoint slide. There's one more procedure in Statgraphics Centurion itself that I wanted to show you today, and that is the t-squared chart. There is a chart in the Statistical Process Control section of Statgraphics, which takes and plots out a statistic called t-squared. Now, what t-squared does is measures the distance of each observation in a big point cloud from the centroid of that data. The centroid of the data being the location of the mean. So, for example, if I was to go back up here to where I did a three-dimensional plot, a point cloud plot, where was it? It was back up here someplace. Remember, I had done a three-dimensional plot for you. There it is, a 3D point cloud. Okay. The 3D point cloud here shows the points plotted with respect to 3 dimensions. The t-squared statistic would in general measure the distance of each of the points, not in 3 dimensions, of course, we're working in 8 dimensions. The distance from each of the points to the centroid of the data. The centroid would be the point of average GDP, average birth rate, and average infant mortality. And in a t-squared chart, we take and compute the distance of each of the points from the middle and plot them out. Now, what's a t-squared chart good for? Well, a t-squared chart is good for potentially detecting outliers. Tell me, not in this 3-dimensional space, but in the space of the 8 variables that I've been working with, are there any outliers? Okay, well, let's go back to Statgraphics for a moment. Okay, and I'm going to minimize some of these other windows as I go along here. One thing that happens as I do a lot of these analyses, when I have a lot of windows open in Statgraphics, they're all keeping a copy of their data. So it's a good idea, and I think I've told you this before, if you're doing lots of analyses, opening up lots of windows, that you minimize the windows that you're not looking at. That will actually give back whatever memory is being used by that procedure and get rid of the multiple copies of the data that are floating around. Okay. I thought I would do that to just take a little bit of the load off the system. I'm now going to go, though, to actually let me call back one of the multiple variable analysis because I need to get the variables. I need to copy these variables again, Control-C. Okay. Now I'm going to go to SPC, Control Charts, Multivariate Control Charts. And the chart I want to show you now is the t-squared control chart. To do a t-squared control chart, I'm going to paste in those same 8 variables, press OK a couple times, and ask it to create for me a t-squared chart. Now, a t-squared chart is going to look like this. It's going to have a point on it for each of the countries. There is a point on this particular chart showing each of the countries. Okay? The line shows me what would be the equivalent of 3 standard deviations away from the mean in that 8-dimensional space of the variables. Any point beyond that line is unusual. It's the equivalent of being more than 3 standard deviations out. Now, it's called a multivariate control chart. I'm not using it for control purposes. I'm using it just to identify unusual points. And actually, to identify the unusual points, I'm going to use my identification procedure, tell it I want to click on points to label them, and let's see who's the most unusual country in my data set. Monaco. For some reason, it appears that Monaco does not well follow the pattern of the other countries. It's far away from the average, the farthest country away from the average on those 8 different characteristics. Also somewhat unusual is Macau and Singapore and East Timor. Okay. So with respect to the 8 variables that I've been looking at, if you wanted to ask me, are there any potential outliers in the data, I'd say, well, you know, Monaco looks quite unusual, so does Macau, so does Singapore, and so does East Timor. Well, that's interesting. Why do they look so unusual? Well, why you can find out by actually going to the Tables and Graphs button and asking for a t-squared decomposition. A t-squared decomposition will take each of those observations, each of the ones that was beyond 3 standard deviations, and show you how important each of the variables are, what their contributions are to the t-squared of that particular observation. Now, the most unusual was row 139. That was Monaco. It had a t-squared value of 50. Now, what it shows is actually, for each one of those variables, how much that t-squared would go down if I got rid of a particular variable. It says, for example, if I dropped out population density, t-squared would go down to 29, would go down by 29.9 units. If I dropped out farmable, it would go down by 24.1 units. Any variable with a high number in that row is a significant contributor to t-squared. So it looks like for something like Monaco, the significant contributors, what makes it unusual are its population density, its amount of farmable land, and, well, to some extent, I guess, perhaps its death rate, and also the contribution of agriculture to GDP. The other 2 countries, Macau and Singapore, those are 123 and 185. Their primary contributions come from population density, amount of farmable land, and to some extent infant mortality and GDP. East Timor, on the other hand, that's 59. It's unusual primarily with respect to GDP and agriculture. So it's nice. The d-squared decomposition, if you do see unusual values, okay, will show you what variables contribute to the fact that that's particularly unusual. Now there's one other plot you might like here. Okay, it's called a control ellipse. A control ellipse will actually take and plot each of the variables with respect to, each of the countries with respect to two variables. Now, it works out nicely, actually, if I plot agriculture and GDP. If I plot agriculture and GDP, you can quickly see the four unusual variables, the four unusual countries. Here is East Timor, here is Monaco, here is Macau, and here is Singapore. The control ellipse is the equivalent 3 sigma limits on agriculture and GDP. The reason East Timor looks unusual is it actually had unusually low GDP given the fact that it had only a moderate contribution of agriculture to GDP. Okay. Gives you a little bit more insight. If I change this and make it instead farmable land and population density, you can see why Singapore, Monaco, and Macau are unusual. Actually, there's two right on top of each other here. They have a very high amount of population density and a very low amount of farmable land. Anyway, it's a very nice procedure, the t-squared chart procedure. It's a procedure that lets me go in and identify unusual points in a multidimensional space. Look for outliers. Okay. Very good. Well, let me for the moment close off Statgraphics Centurion, close that down, get back to my slides on multivariate methods, my PowerPoint presentation, because there's one more thing I want to show you today, and that is the Uniwin package. As I said, there's been a very nice package developed by my close friend and colleague Christian Charles over in France to do certain multivariate statistical techniques that Statgraphics doesn't do. And what I wanted to do is I wanted to take this same amount of data, same variables in countries of the world and so forth, and demonstrate quickly some of the features of Uniwin. Now, one of the features of Uniwin, when it does a principal components analysis, is that it allows you to add in supplementary variables, additional variables not used in the analysis, not used, for example, to generate the principal components. But you can plot them on the same plots as the principal components to see how they would compare. So, for example, what I'm going to load up in a moment is the 8 variables that I've been looking at: population, density, infant mortality, GDP, and so forth. But I've added into the file, into the data file that I'm going to pull into Uniwin, phones. Phones is a measure, transformed, of course, I think I took the cube root of it, of the amount of phones per 1,000 people. I'm going to do in Uniwin the same analysis, the same principal components analysis I did in Centurion, generate the same sort of plots, but then show how phones is related to those principal components. Phones being a variable not used to generate the principal components. Okay. Now to do this, I need actually to escape from my PowerPoint slides for a moment. I need to get back to my desktop and call up Uniwin Plus. Okay, I'm actually going to call up Uniwin Plus version 7.2.1, which is the version that is currently being distributed by Sigma Plus. Now it's going to take just a moment for the program, my computer here, to load Uniwin Plus. As you can see, I've fairly heavily used this particular laptop. It's got a lot of different programs and so forth on it. I'm currently running PowerPoint and GoToWebinar and so forth. So it does take a moment to load any new program that I loaded up. All right. This is the main screen that will come up when you first come into Uniwin, Uniwin Plus actually. What you will see, I think very quickly if you look at the main menu here, is that everything is in French. Believe me, that's not a big drawback. I don't speak any French, but I've been able to find my way around Uniwin throughout the years with very little problem. First thing I would typically do is I'd go to Files on the menu and open up a file. Okay, and the file I want to open, in this case, is going to be in my Webinars folder. Let me see if I can find it. There it is, Webinar. It's called Countries for Uniwin. Now, you may notice that the current version of Uniwin analyzes Statgraphics data files directly. Data files in the SF6 format. Now, SF6 is the format that was primarily used in version 15 of Centurion. But it's actually very easy to save a file in that format. If you're in Statgraphics, you simply say File, Save Data File, and one of the options you have is to save it as an SF6 file. Christian tells me that the next version, version 8 of Uniwin, will open the SGD versions of the Statgraphics files. Okay, but it's very easy right now to just save your Statgraphics files in our SF6 format. Okay, now you can see those countries loaded up with the additional column over here called Phones. Now let's suppose I wanted to do a principal components analysis. I'd go to the menu, I'd go to Describe, Principal Components. It's going to ask me for several things. First off, it's going to ask me, what variables do you want to use in the base? And I'm going to pick those same 8 variables that we've been analyzing here to do the principal components on. It's going to ask me how I want to label those variables, and I'll tell it to label by country. Now that's very similar to Statgraphics Centurion. Where the additional feature comes down is here, where I can tell it that I have either supplemental variables, like phones, that I'd like to plot, or supplemental individuals, supplemental rows that I'd like to plot. You can put in either or both. I decided for purposes of illustration to put in phones. Okay. I'll then press OK, and because I told it that there would be supplemental variables, I need to now tell it what the supplemental variables are. And supplemental variables, incidentally, can be either quantitative or qualitative. In this case, I have a quantitative variable called phone. So I'll tell it OK. And it'll say, where do you want to save the results? Because one thing Uniwin does, when you do an analysis, it saves the results in a file. and it suggests a file, I'll tell it, yeah, you can go ahead and save it there. So when I've done this before, yeah, you can replace what's already out there. Okay? And now, okay, what Uniwin has done is the typical analysis for me. It shows me the percent of variability, as you can see right here, attributable to each of the principal components, and it's done the equivalent of a scree plot by plotting the diagrams. Okay. Now, what I wanted to show you most often, let me push suites here and wait a moment till it comes up with options. If I push this button here, I can ask for a correlation circle. This correlation circle will plot the weights of the principal components. And I'm going to ask for both the base variables and the supplemental variables with points and lines. Okay. It's going to show me the base variables in black, the supplemental variables in red, and I'm going to tell it, yes, go ahead and label the points. Well, now what it's created for me, Uniwin has, is something that they call a correlation circle. It's equivalent of our 2D factor plot, but it's plotted the components on a circle. Okay, because the maximum possible location of the components forms a circle. So if a particular variable was loaded completely as possible on a variable, it would be out at 1. And then we've got 75% and 50% lines as well. Okay, so it's like the 2D component plot, but very nicely, I think, displayed on a circular graph, a correlation circle. The other thing that's unique, though, is you can see points, which was not included in the analysis, as well as the variables that were used to create the plot. I'm sorry, not points, phones. Okay, the location of phones is very, very close, in fact, to the location of literacy. So with respect to these two principal components, phones and literacy and GDP are actually very, very similar. So it's a way, at least, that I can go ahead and locate additional variables on my plot, variables not included in the analysis, to see where they would fall. Very nice feature and something that you can do. A couple other pictures that are also available in Uniwin. That was the correlation circle. And you see you can actually rotate labels around and so forth if you want to see them a little bit better. A couple other plots that you can also make with Uniwin if you do a principal components analysis. One is a scatter plot of the individual countries, where you actually scale the size of the symbols according to what are called the squared cosines. The squared cosine measures how linked a particular observation is to the principal components. If you're strongly linked to a principal component, you're being shown on this particular plot as a large symbol. If you're not very strongly linked, like Fiji here, for example, you're being shown as a small symbol. And you can also do a selection based on those squared cosines if you like. You can ask Uniwin to plot only those values for which the squared cosines are greater than a particular value. So it'll throw out of the plot anything that's not strongly linked, for example, to the first component, and simply plot for you those that are. Another nice additional feature that's available in Uniwin. One other feature of Uniwin that I wanted to show you that's actually related to the principal components in factor analysis that Statgraphics Centurion doesn't have is something called multidimensional scaling. Now, multidimensional scaling is a procedure that's designed to take a set of observations in a multidimensional space, like our countries, project them down into a low-dimensional space, like a set of principal components, where the goal is to preserve the relevant distances, the relative distances between the points. To take our points, for example, in 8 dimensions, project them down to 2 dimensions, distorting as little as possible the relative location of the points with respect to one another. Okay? What's particularly different about multidimensional scaling, though, is you begin a multidimensional scaling not with a set of 8 variables, but with an n by n matrix of either similarities or dissimilarities. So what we would start the multidimensional scaling actually with is a big distance matrix. If I have, for example, 197 countries with complete information about the 8 variables that I've been looking at, and I think about plotting them out in an 8-dimensional space, I need to create a 197 by 197 matrix where the matrix contains the distance between every pair of countries. Okay, now Uniwin will do that for you, by the way. You don't have to create it by hand. But you also don't have to start with variables. There are times where you have a bunch of objects, n objects, and you have a measure of similarity or dissimilarity amongst every pair of objects. And you'd like to plot those objects on a 2-dimensional map to see which objects are similar to which other objects. Okay, so it's actually a little bit more general, although the mathematics involved will be very similar to the principal components mathematics. You can start not with the variables. You could start, if you wanted to, with simply an n by n matrix that identified how similar or dissimilar each object was from another. Now, what I decided to do in this case is I decided to do something similar to what we had done before. I'm going to start with the 8 variables we've been looking at. And actually, in preparing a data file to analyze in Uniwin, the first thing I did is I took and I reduced my data set down to those 8 variables. I removed all rows that didn't have complete data. Because the variables are also measured in different units, while I was in Statgraphics, I used the standardized operator to standardize each variable. The standardized operator in Statgraphics, you can apply it to any column, will subtract the mean and divide by the standard deviation. The reason I needed to do that in this case was everything was in different units. You know, I had GDP, I had infant mortality, I had farmable land, all in different units. It didn't make much sense to start computing distances when everything was in different units. So I standardized everything, so every column would have a mean of 0 and a standard deviation of 1. I then saved a new data file. It's a file called Countries Scaled for Uniwin. This particular data file is also available on our website, on the webinar page on our website, in case you want to work with this. And there is an evaluation version of Uniwin on Sigma Plus's site that you could try. Okay. Now what I'm going to do is I'm going to go back to Uniwin. I'm going to load up those standardized variables. So let's go back, if we can, to Uniwin for a moment. And I need to find my way back to the data file. Here we go. Now, though, I'm going to open up instead a second file. This file is called Country Scaled for Uniwin. Okay. If you take a look at this particular data file, you'll see that this particular data file has a bunch of variables that all have been rescaled. They've all been standardized. They all have a mean of 0 and a standard deviation of 1. Okay? Now, the next thing I'm going to do is I'm going to go to the Edit menu and ask it to create a table of Euclidean distances. I'm going to tell it to take the 8 variables that I currently have and create a new variable called distance. Okay? If I then press OK, it's going to start by taking those 8 columns, population density, infant mortality, all the way down to agriculture. And it's going to create for me a 197 by 197 matrix, which it just did. Okay. I'm now going to ask it to reopen that particular data file. And actually, I don't need that graph right now. I do want you to see the data file. What it's now done in addition to those is added in a matrix of distances. You can probably see out here it created some new columns called distance 1, distance 2, distance 3, all the way out to distance 197. Okay. It's actually just the distances are on the lower diagonal. Okay. Now, to run the multidimensional scaling, I'll go to Describe, Distances, and Dissimilarities. Okay. This is where I actually go to run the multidimensional scaling procedure. Okay. I'm going to tell it that what I want it to analyze are the columns distance 1 down through, come on down there, through distance 197. To use country to identify the individuals, and then I'll press OK. As usual, it's going to save the results out there in a file for me. Wants to know if I want to replace what's already out there. I'll say yes. And it's now going to perform the multidimensional scaling. Now, the multidimensional scaling, well, what it actually performs is what's called metric multidimensional scaling, is equivalent to extracting the principal components. What's really different, though, is it started with a matrix of distances, a matrix showing the distances between all pairs of the 127 countries. Now, there are a couple of graphs that I can ask it for, and we'll get there in just a moment. One graph I can ask it for is a plot of the individuals. Okay, and here is a plot of all of the countries, the 197 countries, the same that we've been looking at all day long. But the interesting thing here is it did not start with the correlation matrix. It started with a matrix of distances and has now managed to project into 2 dimensions the relative location of those countries with respect to each other. And again, you can see out here Hong Kong and Macau and Singapore as opposed to countries like Somalia, Liberia, and Sierra Leone. I can also ask it for a distance plot. This is the last plot I'm going to show you. Something else that StatGraphics doesn't show you, okay, but is quite useful from the point of view of multidimensional scaling. It takes a minute to display this plot. But what it will do is it will now take every pair of points, each pair of that 197 by 197 matrix, and plot the calculated distance, which is the distance between each pair of points when it's projected down into 2 dimensions, versus the observed distance, which is the distance that we calculated for the 8 dimensions. There's an R² of about 97% here, which is a measure of how distorted things are. And for most pairs of countries, the observed distance is actually quite similar to the calculated distance. So for most pairs of countries, we haven't distorted their relative placement much by projecting them down into 2 dimensions. There are some pairs, though, that were somewhat distorted. For example, if I look at this particular pair right here, okay, and when I click on it, you can see in the upper right-hand corner what pair of points that is. That's actually Liechtenstein and Monaco. They are calculated to be very similar in 2 dimensions, whereas in the original 8 dimensions, they were actually fairly far apart. But that's not surprising, I suppose. Monaco was one of those outliers. So, it's not going to be all that well represented by a projection down into 2 dimensions. Well, that's a quick view of some of the things that Uniwin can do. And I've probably gone a little bit over the hour-and-a-half that I promised. So it's actually time for me to finish up now and start taking some questions. If you'd like more information about what I've shown you, the main website for StatGraphics Centurion is www.statgraphics.com. If you'd like information about Uniwin, you can go either to www.statgraphics.fr or www.sigmaplus.fr. If you have comments, questions, suggestions, whatever that you'd like to email to us, the email that we would suggest you send things to is info@statgraphics.com. Okay, that will end my formal presentation, and it's very encouraging to see that most of you who started about 2 hours ago are still with me. I hope that means that you found things to be interesting. Okay, let's see what sort of questions that I have gotten and see how I can comment on them. Okay. Thank you, though, for all of you staying around so long. I know that if you are in Western Europe, and we did talk a little bit about Western Europe, you're probably getting pretty hungry right now. Anyway, question 1. You referenced the book on multivariate analysis and said that it explained the methods used in StatGraphics. Are there any other books you'd recommend for the other information? Well, one thing you should be aware of, I'm not sure if you are or not, is that while you are in StatGraphics, there is a PDF file that you can access called References. I'm going to load back up StatGraphics for a moment. I'm going to go to the Help menu, and if you go to Help Procedure Documentation, it will list a lot of PDF files that are shipped with StatGraphics. One of those files is actually called references.pdf. If you open that, you will see a large list of books that were used to develop the procedures we have in StatGraphics. And I believe there probably is a section, I'm not positive, but I think on multivariate statistics. Yeah, there it is, multivariate methods. You'll see a list of, I think, something like 10 books. There's a very well-known book by T.W. Anderson, An Introduction to Multivariate Statistical Analysis. You see the Johnson and Wishern book there. There are some books solely on principal components analysis. And a book by Stevens called Applied Multivariate Statistics for the Social Sciences. So there are quite a number of textbooks, and the ones that we've used most extensively in developing StatGraphics you can find in that references.pdf file. Okay. Let's see, what other questions? Can you apply PCA or factor analysis to time series data or time series variables? Or will this be covered next webinar? You know, that's an interesting question, and I don't think I have a good answer for that. But I will certainly do some research on that and comment on it on the next lecture. Can you use PCA, principal components or factor analysis, in analyzing time series? My initial guess is that you can, but I'd rather do a little research and give you a more definitive answer in the next webinar. Question 3. I may be getting ahead of myself. If you have equally spaced time series, is this useful for helping reduce the dimensionality for when you're doing forecasting? Well, someone else is interested in doing this for time series analysis. Again, I'm going to do some research, and hopefully I can come up with a good example of how it can be used. Why t-squared chart didn't coincide with the control ellipse in terms of the 3 sigma line? You know, one of the things I showed you in my PowerPoint presentation when I looked at the t-squared chart is I showed you initially a plot of t-squared with respect to all 8 variables simultaneously. And to be beyond the 3 sigma limit on a t-squared chart, you basically had to be out of whack or unusual, far away from the middle with respect to all 8 of the variables. When I showed you these control ellipses, okay, the ellipse there is the equivalent 3 sigma point, or 99.73% containment ellipse, if you like. The ellipse that would contain 99.73% of the observations if the data on only population density and formability came from a multivariate normal distribution. These are incidentally dependent, these limits and so forth, on the assumption of a multivariate normal distribution. And the position of each of the points on this ellipse is their distance from the centroid only with respect to whatever 2 variables are being plotted on the control ellipse. So you can be unusual, for example, with respect to all 8 variables, but not unusual with respect to a particular pair. I was using the control ellipse as a follow-up to try to understand why particular observations were coming up as unusual back on that original t-squared chart. And of course, if you're out of sync or unusual in 8-dimensional space, it's not usually because of all 8 variables. It's because of a couple that are pushing you out. And I was using these control ellipses to suggest that Singapore, Macau, and Monaco were showing up on the t-squared as being unusual because of primarily farmable land and population density, because they do look unusual on that control ellipse, whereas East Timor does not. But where if you looked at the control ellipse on agriculture and GDP, East Timor was the unusual one. Well, Monaco almost as well. But the primary reason that East Timor showed up on the t-squared chart was because it was unusual with respect to the joint distribution of agriculture and GDP. Okay, so you can show up as unusual on the t-squared chart, but not on every possible 2-variable control ellipse that I could create. Okay. Let's see, question number 5. Is it advisable to use standardized assuming normality over Box-Cox? Actually, you need to use both. What the Box-Cox procedure did for me was to basically get rid of the skewness in the data. Right, let me just load that data set back up again for a second where I started. That was countries of the world, the original one, before I did any transformation. This was the data in its original units. And look at something like infant mortality, okay? Infant mortality is the number of deaths before year 1. It's the number of babies out of every 1,000 births who died before they were 1 year old. Now you can see some fairly awful numbers in places like, who's first here? Afghanistan. Afghanistan, in this particular data set, had 163 deaths per 1,000 births. Okay, countries like Australia, for example, had less than 5 deaths per 1,000 births. Huge differences. If I did something like a histogram, let's just go in and do a quick histogram of, infant mortality. You'd see, I'm quite certain if I do this histogram, it's going to be skewed to the right-hand side. Yeah, there it is, right? Quite skewed. And unfortunately, what that means is if I use infant mortality as a variable in my models, most of the data, the vast majority, are very similar to each other, whereas there's only a few that are unusual. And what those few are going to do is they are going to have a disproportionately large impact on my models. Okay? Or if I took something like GDP, per capita GDP, and looked at its distribution, it's also highly skewed. Well, for a lot of factors, although I might measure the GDP, right? GDP itself, well, doesn't necessarily capture the real effects. For example, if I looked at the difference between a GDP of 5 and 6, that's probably not as different as or doesn't have the same impact as the difference between 55 and 56. the effects of a lot of my variables are really not additive anyway. When I do a Box-Cox transformation, what I'm doing, for example, is taking something like a log of GDP, okay, in order to make the distribution more symmetric, to spread out the observations so that all the countries will enter better into my model. However, taking the log of GDP versus the log, for example, of infant mortality still doesn't put things in the same units. And if I take the log of infant mortality, okay, that probably gets rid of the skewness, I hope, on infant mortality when it decides to do it. There we go. But you can see the units are still a lot different than the units of log of GDP. What I did is I did both things before I went to do the multidimensional scaling. I took the log and then I standardized the logs. What that's going to do is that's going to force everything to have a mean of 0 and a standard deviation of 1. So if I do that on infant mortality and do the same thing on GDP, not only have I gotten rid of the skewness, but I've put them all on the same scale by, after getting rid of the skewness, getting them back to a mean of 0 and a standard deviation of 1. So you really have to do both of those things to condition that data if you're going to do something like a multidimensional scaling, where you're going to compute a distance matrix and try to show the distance between all pairs of observations. Okay. Hope that answers that question. Okay, question number 6. Is it possible to use the analysis of multivariate contegration by using this analysis? Well, that's something I'm not actually familiar with, so I'm not going to be able to answer that. I can look that up too. Multivariate contegration. Probably means something that I know by some other name. Oh, and Christian actually sent me a comment about principal components for time series. Christian says that with Uniwin, you can analyze time series data by either doing a multiple factor analysis or by using a procedure he developed called status. Status is something I'll show you in a future seminar, which analyzes three-way tables where the third dimension is time. It will take the variables and actually project the variable trajectories over time. Okay, that's going to be something I'm going to want to dig in to myself before the next webinar. Well, that takes care of the questions. Any questions that you think of after the seminar is over, you can go ahead and send them to us. I'll make up a document and eventually put it on the website, on our webinar page, with answers to some of the things I actually said I would look up for you, and also any other unanswered questions that you send in. Again, I thank you for your patience. The next webinar, I believe, is scheduled for December 4th. The major topic of the next webinar will be sorting and grouping of multivariate data. We'll be looking at cluster analysis. We'll be looking at discriminant analysis. And one of the interesting things you'll find is that when we do the cluster analysis, Doing a cluster analysis, we'll do it both on our original 8 variables that we looked at today, but also on the principal components. And you'll see that by taking the principal components first and doing cluster analysis on the principal components, that actually the results of the cluster analysis are more understandable than they are if I do it on the original variables. So thank you for your patience. I look forward to seeing you all, or at least talking to you all, again on December 4th.